Hi, my name is Sam Rumack, and I'm president of the University of Michigan MRover team here in Ann Arbor. MRover is a multidisciplinary organization with about 30 active members from both engineering and non-engineering backgrounds. Our team is split up into 3 main units: the mechanical, electrical, and our newly formed science team. We've been working hard this past year to design, build, and test a rover fit to compete in the 2017 University Rover Challenge, and we're excited to showcase this year's design.
On this year's rover, we have a carbon fiber chassis which connects to all subsystems. Here we have our rocker bogie suspension, which connects to our 6 wheels with in-hub motors. At the front of the chassis, we have a 6 degree of freedom robotic arm that's mounted via adjustable brackets. We can remove these brackets and mount our soil sample return system. At the back of the chassis, we have our electrical box, and on that frame houses our 4 omnidirectional antennas at 2.4 gigahertz and 900 megahertz. Here we have our stereoscopic camera, which is for vision and point mapping. The suspension is a rocker bogie design inspired by the Curiosity rover. It contains carbon fiber tubes epoxied to aluminum joints and a differential bar connecting the suspension to the chassis. This passive suspension allows for all 6 wheels to be in contact with the ground at the same time, and the differential bar balances out the angle of the chassis.
Connected to the rocker bogie suspension is the drive system of the rover, which contains 6 wheels with in-hub motors. The motors that drive the wheels will provide enough torque to drive up 60-degree inclines that we expect to be present during the extreme retrieval and delivery task. Our drive motors come equipped with optical encoders, which will allow us to have more control over the drive system and prevent wheel locking and slipping from occurring. In addition, we have produced custom rubber treads, which will provide more traction in slippery and sandy environments.
The robotic arm has 6 degrees of freedom and approximately 35 inches of reach. At the base, the arm rotates in the horizontal and vertical directions to be able to pick up objects and place them in the desired location. The body of the arm is made up of parallel linkage systems, which house the transmission and motors for the remaining joints. This design reduces the risk of interference between the arm, wiring, and the rest of the rover. The hand is comprised of 2 interlocking scoops which open and close in place.
This year, we have completely revamped our rover's embedded software, leveraging the Robot Operating System, or ROS, a framework for robotic operation. ROS is a collection of tools for passing data between different software modules using a network interface. Additionally, it includes tools for creating a virtual environment to simulate the rover's functionality. This year, we are introducing 2 new modes of operation, autonomous mode and autonomous recovery mode.
The core of the autonomous mode uses the tangent bug algorithm. In this method, we draw a straight line from our rover to the goal state, and then we navigate around any obstacles along the shortest path to that line. Using a technique known as SLAM, or simultaneous localization and mapping, we can take our stereoscopic camera, as well as data from our ultrasonic sensors, and build a map of the environment around the rover, in which to identify these obstacles. In the event of lost comms, we can use these maps to navigate the rover autonomously to a known good location. This year, we are using the 900 MHz band, as well as the 2.4 GHz band, with 4 orthogonally placed antennas on the rover. In addition, several of our members are amateur radio licensed, giving us access to a 3rd amateur radio band. This is done so that if any of our links fail, we can safely fail over to another one of our links.
Our soil sample return subsystem is broken into 2 main systems: sample collection and cache analysis. The sample collection system is an auger attached at the end of a linear actuator that, when plunged into the ground, can drill at more than 5 centimeters. The cache system contains 3 different boxes for both onboard and offboard testing. It's mounted on a Geneva drive, which allows the operator to easily position the cache boxes.
Analyzing imagery of the competition site from the Landsat 7 satellite, we're able to narrow down potential soil sample locations, those most likely to harbor life. We focus on environmental factors such as soil humidity and composition. On-site, we'll be performing 3 tests: soil temperature, humidity, and conductivity. These 3 quick tests are designed to determine whether a sample needs additional analysis off-board.
As you have seen, we have already implemented a large part of the functionality required to compete successfully in the 2017 University Rover Challenge. Moving forward, we still need to finish manufacturing the soil sample collection mechanism, as well as performing more rigorous testing of individual systems, as well as the full rover during our planned simulated competition in late March. We are confident that we can perform well in the 2017 University Rover Challenge. On behalf of the Michigan Mars Rover team, thank you for your consideration.